Hi everyone, I hope you're doing well. In this video, we'll talk about LLMs evolution for the period from 2017 to 2025. We talk about some LLMs families, how these LLMs are built in general, how they are used and how they can be augmented. We talk about evaluation and some datasets used for this evaluation, and we will finish the video with talking about future directions. So let's start with looking at some LLMs families. We have the GPT family developed by OpenAI. This includes auto-regressive models like GPT-3 and 4. We have the Llama family released by Meta. It includes open source models, foundation or chat models. And as these models are open source, they serve as a baseline for widespread research and fine-tuning. We also have Palm family developed by Google, and we also have other famous models such as Flan, Gopher, Bloom, and the well-known Gemini family. Now let's take a look at how these models are built. First of all, these models need data, and of course this data needs to be prepared. Among the preparation, we have what we call data filtering, where noise, outliers, and irrelevant text are filtered. We go through the process of deduplication, which is the process of removing duplicates from the dataset, and we remove them to prevent the model to be biased towards these duplicates or memorize specific examples more than others. Also, tokenization is processed, which is about breaking text into smaller units that we call tokens. Among the algorithms to tokenize sentences, we code what we call BPE for byte pair encoding. We have word piece, and we have other ones that I don't necessarily mention here. It's to be noted, guys, that the idea here is to provide a high-level overview of the evolution without delving into granular details about any concept. But don't hesitate to ask me questions in the comments if you need more details on any concept. So apart from the data preparation, choosing the model architecture is part of building the LLM as well. These architectures are derivative of the transformer architecture, which is composed of an encoder and decoder. So this is the encoder-decoder architecture, is the original architecture presented in the transformer paper. Models like T5 and BART inherited the same encoder-decoder architecture, and it's generally used to handle sequence-to-sequence tasks like translation and text summarization. But other architectures are based on the encoder only, like the one used in BERT model, and this is more used for tasks like classification. Other models, like the GPT family models, use only the decoder, and these models are more used for generative tasks. Another information is crucial when building this kind of models is the positional encoding. And this is crucial because it permits to inject sequence order or words order in the sequence. And this is crucial because it's used to inject sequence order information during the model training. And to inject this information, different type of embeddings can be used. The first one that appeared are called the absolute positional embeddings. These embeddings are static and might be irrelevant in some complex use case without going into the details. This is why the relative positional embeddings appeared, and these ones encode the pairwise distance between tokens. And we have also the rotary positional embeddings, which incorporates relative distance information as well, but using rotation matrices. Now, as we talked about training, there are actually different steps in training. The first one is called the pre-training step, where models learn from massive unlabeled corpora, and the task that they learn in this step consists on predicting the next token in a given sentence. And this is a cheap step, guys, talking about data preparation, because we don't need to use labeled data for this step because we just need to have simple sequences of words, and we ask the model to predict the word following a chosen word. After the pre-training step, we have what we call fine-tuning steps, which permit to fine-tune the pre-trained models resulting from the previous phase on specific tasks, and they can even be aligned with human instructions. And talking about alignments, many techniques has emerged in the recent years. Among them, we quote the RLHF, which stands for Reinforcement Learning from Human Feedback, which, as its name indicates, there is a human feedback in the training loop. This human feedback forms what we call preferences dataset, and this dataset is used to train a reward model, which will give feedback to what we call a policy model, which is going to be our final model. So here again, I'm going very high level into this process, but don't hesitate to ask me questions in the video comments if you have any. Another technique has emerged after the RLHF technique is the DPO, which stands for Direct Policy Optimization. Here, one of the biggest advantages is that we don't need a reward model to be trained, and the human preferences are used directly to train the policy model. Now, we can't talk about training without talking about optimization, which tends to optimize computational resources during model development and deployment. One of the most famous optimization technique is called LoRa adaptation for low rank adaptation, and this is actually a parameter efficient fine-tuning, or PEFT for short. And this technique is efficient because only a part of the model weights are updated instead of all of them. Also, we have what we call the knowledge distillation. Here, there is a knowledge transfer from a large model called the teacher to a smaller model called the student. And this transfer learning improves the student performance. Also, we have what we call quantization. Quantization consists on reducing the precision of model weights. For example, going from a float 32 to integer 8. We agree that precision and accuracy decrease because there is a loss of information in this quantization process, but this decreases the model size and latency during inference. Now let's talk about usage and augmentation. And here we quote one of the techniques that has emerged in recent years. This technique called prompt engineering. This technique is as simple as crafting inputs to guide the model's output. But at the same time, this crafting is critical because it will shape the model reasoning in some way. And sometimes simple prompting doesn't give us the desired answer. This is why more complex prompting techniques appeared. Among them, we quote what we call chain of thought, or COT, which permits to decompose complex problems into intermediate reasoning steps. We have what we call the tree of thought as well, or TOT for short. This allows the model to explore multiple reasoning branches, evaluate these branches, and find the best solution to answer the query. Another PE technique is called self-consistency, where the model generates multiple responses to the same query, selects the most consistent answer, and selects the most consistent answer to improve accuracy. Last but not least, we have reflection, where we prompt the model to evaluate and revise its own outputs to correct errors and improve answers quality. So at this step, we agree, guys, that prompt engineering is priceless because it helps us to guide the model in his reasoning. It even adds the possibility to inject new data or new information, what we call in-context information, apart from the data that the model has learned during his pre-training. But the problem here, what we give in the prompts till now, we add them manually. But what if we need to inject information from external sources? And here is why models augmentation appeared, because it enables us to augment LLM's knowledge through external knowledge. And among the most used augmentation techniques nowadays, we cite the RAG technique, which stands for Retrieval Augmented Generation, where the model retrieves relevant data from external sources to add them in its context and answer to the user query. We also have the tools used to extend the model's capabilities, and these tools can be APIs, search engines, or even custom functions that you code by yourselves. And this tool use is actually part of the RAG technique, because we can add any information coming from these tools calls to the context given to the model, which will be used to provide an answer to the user. And of course, we cannot not to talk about autonomous agents, which became ubiquitous nowadays. These actually are AI agents where LLMs act as brains that can perceive, reason, make decisions, and execute actions based on all this process. But now, guys, let's say that our models are ready to be used, but also we need to evaluate them to see how they perform. To do so, many benchmarks are available. To name a few, we have the MMLU benchmark, which is used to evaluate the model language understanding. We have the GSM-8K, which is used to evaluate mathematical reasoning. And we have the Human Eval benchmark, which is actually for coding and programming. Also, we have metrics that are used to measure the performance of these models. Among them, we have the exact match. As its name indicates, it's actually used to evaluate strict accuracy. We have the pass@k metrics, which measures the probability that at least one of the k generated answers is correct. Also, we have the Rouge metric, which is used for summarization and translation. These are some of the metrics which are commonly used, guys, but there are far many others in the state of the art. Also, models can be used to evaluate other models as well, and this is what we call LLM as a judge, where another LLM is actually given instruction to evaluate another LLM performing on a certain task. Now, let's take a look at future directions in this field. It's to be noted that small language models, or SLMs for short, are emerging because once they are smaller, so they are more efficient and cost effective, either in training or inference. Multimodal models are emerging as well. These models can process and generate natively different types of outputs like text, images, audio, and video. We have what we call the post-attention paradigms. Post-attention because these are actually alternatives to the transformer architecture. We have some models like SSM for state space models, or the MOE for mixture of expert models. These models are known for handling longer contexts. Now, we cannot finish the video without talking about security and ethics. This is crucial, guys, because these models need to be secured against attacks like adversarial attacks, and it's important to mitigate biases that might be learned during training before releasing this model to the public. So this is it, guys, for today. This was a high-level overview of the evolution of LLMs during the last few years. Each concept that I talked about in this video can be explained in a separate video by itself. So don't hesitate to ask me questions in the comment if you have any. I hope you liked the video. Please don't forget to subscribe to the channel, and see you next time.